Well, welcome everyone. My name is Russ Sorrells. This is IndustryCast, where we go live 11:30 every Wednesday to talk about concepts, ideas, technologies, manufacturing process improvement ideas, how to help our customers be more effective in their roles as manufacturing engineers. That's what our mission is. Our focus is to always be adding value. And one of the ways that we do that is by offering these free webinars that essentially just share content. This isn't us advertising and promoting ourselves. It's literally trying to share knowledge in a way that's going to be meaningful for our customers. So today we're going to talk about leak testing. And I'm going to run through a lot of information in a very short amount of time to cover some general ideas on leak testing, help people kind of wrap their mind around what is leak testing, different leak test technologies that exist, and so we're gonna talk about that. And this is in preparation for a longer version of leak test training that we're going to be conducting over the next 3 months. So we're going to be doing multiple training sessions over the next 3 months, and we look forward to the opportunity to have a more extended discussion about these technologies, pressure decay, mass flow, tracer gas technologies that Cincinnati Test Systems, which is a company that we've been representing for over 20 years, is an industry leader. CTS is the largest leak test company in the world. They have divisions all around the world and are able to do and apply every leak test technology that exists. So with that, we're going to jump right in. If any questions come up, Matt, if you could just monitor the talk chat room there, if anyone asks any questions so we can get those answered, that would be great. But we're going to rock this out. Okay, so the first concept that everyone needs to understand is that everything leaks. Everything leaks. So the reason that we have airbags that do not deploy after, say, 20 years of being in a steering column is because the charge leaked out, depending on the type of airbag that company used. Everything leaks. So that jar of peanut butter, believe it or not, even though the peanut butter doesn't come out, if you put another fluid in there, it's going to leak out depending on how you turn it. So everything leaks, and that is a concept that is tough for people to wrap their arms around, their mind around. We had a customer the other day that wants to test a gas valve, and that gas valve is obviously it's important that we don't leak gas, because gas is flammable and that could cause a catastrophic event to occur. So we want to make sure that is not leaking. So the technology that you apply to make sure that a gas valve doesn't leak is different than a technology that you would apply to make sure that oil doesn't leak out of your engine, as an example. So applying the right technology is really important. So we're going to understand that. But everything leaks. The question has got to be, how much is too much? So, and that's going to establish our accept reject criteria, which we'll talk about and we talk about throughout the training. So leak and flow testing applications specifically, in case you're not familiar with leak and flow testing, from a medical perspective, you've got any device that is going to take a fluid from the body. We're going to make sure that gets leak tested so that fluid stays in the container that it's supposed to stay in, or the tubes that it's supposed to stay in, or the connectors are connecting and not leaking. So medical, there are just a myriad of medical applications. Automotive, of course, you don't want your radiator fluid to leak. You don't want your oil to leak. You don't want your brake fluid to leak. You don't want your fuel to leak. So all of those things, and you don't want your headlamps to leak, right? So that's the contrast from fuel leakage, which again has a catastrophic event associated with it, versus a headlamp, which just is annoying when water builds up in your headlamp. But those are two products that get leak tested. Sunroofs get leak tested. So everything, you'd be amazed at how many things on your automobile actually get leak tested. Appliances, of course, the valves, your washing machine, the pumping package, your dishwasher. Everything in your dishwasher is getting leak tested as well. reservoirs that are in appliances. Your refrigerator is leak tested. You've got to leak test the ice maker circuit, and you've got to leak test the compressor circuit as well that actually does the cooling for the refrigerator unit. So it is there are multiple applications for leak testing that you may be surprised to understand. So here are some of the reasons why we test. Obviously, we want to make sure that the part functions as it was designed. We want to leak test in process sometimes when we're assembling a product. We don't want to get to the end of the assembly process and then learn that the assembly is not good because it is leaking. So if there's an opportunity to do an intermediate leak test, we want to do that to ensure that we don't waste money in building the product out that is actually a failure. We want to increase and improve reliability, product reliability. We want to minimize liability. That's that airbag concept, right? We know that it's really important that those airbags actually do their thing because they save lives. So we want the products that we are testing to last a long time. And that's the whole liability aspect. Customer satisfaction. It's important that that when your customer gets it, that it's not leaking. They're going to be disappointed, dissatisfied, frustrated when there's an oil leak that that occurs on their floor. And we want to protect the environment. So I can think of some really caustic applications, which are electrical components. So those large electrical components that are on the telephone poles, those are full of caustic material. We don't want that to leak out and harm the environment because of the leak. And it's really nasty stuff. So we want to control the manufacturing process. So early detection of deviations and problems that occur. What is a leak? So from a definition perspective, an emission or release of a material resulting in flow. So that's normally caused by a hole or permeation. From a Reader's Digest or a Webster's perspective, to pass through a hole or a crack in a retaining or excluding wall or container, a small hole or crack through which something can pass. So that is again the definition for a leak. And then we want to know from a leak rate perspective, that's a mass of material that is invading or escaping at any given flow over a given amount of time. So pretty straightforward. That's the definition. And from a cause perspective, porosity, if you do aluminum die cast, if you've seen or experienced aluminum die cast, porosity or pinholes that can occur, either those get exposed they often get exposed during a machining operation when they most become visible. I see them all the time, or have seen them frequently in threads. So you'll thread the part on, but the thread itself will have porosity and a leak will come through that area. Incomplete welds. So if you have brazing, soldering, bonding, gluing operations that are incomplete or leave some holes or variations there, that could obviously lead to a leak. Improper seating of components. You got an O-ring, doesn't seat properly. Improper bolt torque or tightness could be an issue. Missing components, faulty gaskets, surface finish issues also cause leaks, and then improper machining, not allowing proper stability. Yeah.
Quick question there. You touched on it really briefly. You mentioned permeation. You also mentioned gaskets. Can you talk a little bit about diffusion through a material and how that's different than how people think of a typical leak and how it might affect you when you're trying to do leak testing?
Yeah, for sure. So when we think of permeations, sometimes we want so companies come up with a fabric and they want air to escape, but they don't want air to come in. So when you're flow testing, so you're leak testing, something like that, that is one permeation concept that comes to mind as far as we want flow out, but we don't want flow in. So that some in woven materials, things like that, we see permeation from that perspective. Permeation and filtration is another challenge, another area. Does that answer? Is that helpful?
Yeah. I was also thinking, even on the tracer gas side, helium will go right through a rubber balloon. Would some people would say, okay, my balloon must be leaking at the spot on the bottom where I have it tied off. No, the helium is actually going right through the material. So,
Yeah, great
permeation is
point.
different than a hole.
Yes, thank you so much for sharing that. Yeah, so that's exactly right. So that balloon is leaking. Technically, it is leaking the media that is inside of it, and the size of those helium molecules, as that stretch balloon is allowing the helium to permeate out. Exactly. So wonderful example of that. Of how that permeation works. So technically, it is leaking the gas, but if you dunked it underwater, you certainly wouldn't see any bubbles coming out, right?
Yeah, exactly.
Excellent. Did you have one more thought?
Nope, I'm good.
Okay, excellent. Yeah, just keep adding in any insights and in feedback. Super helpful. So leak measurement. So how much is leaking, and is that leaking too much? That's the key that your product engineers really need to figure out. And if they get that right, it will ensure that your customer receives a part that is not defective or going to cause problems, and it will help to minimize the amount of manufacturing scrap that occurs. So there's that fine line of how much is too much, and making sure that process that you define, of course, ensures quality parts getting shipped to your customer, but yet does not create a lot of scrap in your manufacturing process. So that's what we're looking to our product engineers to come up with. And a lot of times there's not the easy thing to do is say no leak, like that gas valve, no leak, the zero leak. Well, as we talked about in the very first slide, everything leaks. So what is the reality of the reject criteria that we're going to have to establish? So how much is too much is the question that is always asked. So depends on what is the required. I'm sorry. So the acceptable levels are going to be based on the following, right? The required test specification, that's going to be your product engineers are going to have that feedback. They're going to put that out there for you. And so what are the consequences? So is it a heart catheter, fire extinguisher? Matt, you and I talk about fire extinguishers fairly often. So what is the criticality of the leak? Obviously, if it's a heart catheter, that's going to be very critical. It's really important that does not leak. If it is a bucket, then it's probably not critical that there's not going to be life in danger as a result of something leaking. So what are the consequences of leakage? Catastrophic failure is or thermal event is a conversation that they have in the automotive world.
Yeah, and you've got pacemaker listed here. So an implantable pacemaker, if during the lifetime of the patient, just one drop of body fluid leaks into the pacemaker can stop. So that can be an instant catastrophic result, right? So
absolutely, yeah, great point.
Pacemaker manufacturers are their leak criteria has 9 or 10 zeros after the decimal because they want to be very, very sure that you don't have that catastrophic event. So if that's your mom or dad with a pacemaker, I'm sure you want that too.
Yeah, and that's an excellent point. And what's interesting is you contrast that with like an automotive headlamp. And so an automotive headlamp is not super critical that it doesn't leak. It's still, going to function as long as the water doesn't ingress into the electrical components and cause some problems from that perspective. But the way that we would test and the cost of the test for an automotive headlamp is a lot simpler and a lot less costly than that pacemaker leak test system because of the sensitivity required to make sure that that pacemaker or that is not leaking. So that's kind of the differences in the technologies and methodology. And then what is important is that hopefully you can rely on us as leak test professionals to help you identify what the right technology to apply for your application. That's what we bring to the table as well. And then after you go through this training, it helps you to make that decision as well. So the nature of the fluid, is it gasoline? Is it chlorine? Is it a gas? What is it that that you're trying to contain in the container? And then the cost to test. As I mentioned, it costs a lot less to test an automotive headlamp as opposed to a pacemaker. So what are the objectives, the budget, the speed? How is the operator going to interface? Is it automatic? Is it manual? Do we need to locate where that leak is? Do we need to quantify the results, or is it just a go, no go, pass fail type of situation? What is the operating environment in which this test process is going to be conducted in? Is it going to be in a hot and cold manufacturing facility? Is it in a controlled clean room? What is the environment is that question. So these are just some of the questions that need to be answered in order to determine what the appropriate technology is for your test application. So as it relates to leak test techniques, so here are some basics. So the basic techniques, you've got bubble testing, you've got acoustic or ultrasound applications. So you might have seen some of the Fluke. I think Fluke has a device that it's like an iPad, and you just move it to your facility. And if there are air leaks, which are obviously pretty significant, it actually exposes those through acoustics. And so those are the basics. Those are the simple applications that are out there, less expensive, but more operator dependent. And then we move into the intermediate technologies. We got pressure decay and mass flow techniques and strategies. So pressure decay, vacuum decay, and mass flow. And then the more sophisticated applications that are more sensitive and going to test those more challenging applications are going to be the sniffer tracer gas technologies, which Matt is an expert in. Maybe tracer gas accumulation, which we're going to hit on, and then the hard vacuum mass spec technology that is what we're going to use for the pacemaker as an example. Here is a graph that can help to wrap your mind around these different technologies. So mass flow, pressure decay, we're looking at 0.6 SCCM down to, nowadays we're able to get with differential pressure decay, we're down in the 0.3 to 0.2 standard cubic centimeters per minute, depending on the application. It's very application dependent, but in some situations where we've got a very small volume, we are able to reach very small leak rates or reject criteria. Bubble testing is actually more sensitive than mass flow and pressure decay technologies. Bubble test, dunk stands. So when the bubble test, we're talking about spraying on Snoop as a media to use. And then the helium sniffer probe as well. Then you've got the helium. Yeah.
I want to touch on something on the bubble test.
Yeah.
There's some caveats to it being more sensitive than mass flow or pressure decay. The first problem is it's much more operator dependent. You have to look for bubbles. You have to distinguish bubbles that were formed from using your spray bottle versus bubbles that were formed because of a leak. The leak has to be small enough that it didn't blow the bubble solution off the leak before it could form a bubble. If you're in a dunk tank, you have to have a part geometry that allows the bubbles to be released and that they don't accumulate under the part or in the fin pack of a heat exchanger coil. So there's a lot of caveats there with this chart. A bubble test can be as good as that, but in reality, there's a lot of things you have to worry about.
Absolutely, and thank you for touching on that. when I started as a manufacturing engineer at Cummins Engine Company all the way back in 1994. And one of the first things that I learned was from the quality engineer. He said, 100% of inspection is only 70% effective for us. So always keep that in mind, because every fix in the manufacturing world sometimes comes with an inspection. Oh, well, have the operator look at it, mark it. That's why when you pop the hood on your vehicle, it looks like the rainbow, because everybody's marking their parts as they are assembled or tested. So, but yeah, great point. 100% inspection is only 70% effective. So, helium mass spec accumulation. We're going to touch on that a little bit here in just a minute. How are we doing on time? Oh, we got about 9 minutes. So that helium accumulation is where we are using a chamber. It's similar to hard vacuum in that we are typically evacuating the part. We're going to backfill the part with some type of tracer gas, but we are not pulling a hard vacuum around the part. We have probes in a chamber where we are looking for helium to accumulate in that chamber. And then that measurement of the background is going to allow us to determine, is this part good or bad? So anything to add to accumulation technology, Matt?
No, I think we're good.
All right. And then this is specific to Cincinnati Test Systems. We have a patented technology that is the purging clamshell. And the purging clamshell allows us, it's a variation of helium accumulation, but we are controlling the environment around the part using a shield gas, essentially similar to like a laser welding, but we use a shield gas that is nitrogen to create a stable environment around the part that we are attempting to test. So that technology has proven to be a very sensitive and more cost-effective method than the next method, which is helium hard vacuum mass spec, which is the most sensitive technology that we have. It is also the most expensive, typically the most expensive technology that we have to apply. But the beauty of utilizing tracer gas is, I mentioned some of the questions that we ask when determining which technology to apply. If our facility is hot and cold, hot and cold, hot and cold, well, utilizing pressure decay or a mass flow technology can be a challenge in that environment. And the reason is, when we use pressure decay technology, we are measuring pressure change inside the part. And so when you're measuring pressure change, I want you to think of a gallon of milk. And that milk jug, that empty milk jug, when you put it outside and the sun shines on it, what happens to it? It expands. And so that expansion is obviously a pressure change. That's the same thing that's happening when we're doing a pressure decay leak test in a facility that has temperature variations and temperature issues, temperature challenges. It's difficult to get a repeatable test if it's in a harsh environment. So tracer gas technology is not sensitive to those temperature variations. It allows us to conduct a test with accurate results, repeatable, and gives us a high level of confidence that if it says the part's bad, it's a bad part, as opposed to sometimes in those more challenging environments, we get a reject and we're like, oh, is this part good or is it bad? Well, let's take it over to the dunk stand. Let's verify that it is a bad part, because of the lack of confidence that can occur in those difficult environments. Anything to add there?
No, I think we can keep going.
All right. So here's just a quick. This is bubble testing, right? So we pressurize the part, we dump it underwater. Pretty straightforward technologies there. We talk about some of the sensitivity, but like Matt talked about, there are many drawbacks associated with using this technology because, great story. We were at a company, this is up in Michigan, and they made fuel rails. Obviously, a fuel rail, pretty important that fuel rail doesn't leak, because that's what makes a thermal event happen. Thermal event being or fire. So this customer was using dunk test technology. And when we were meeting with the customer, we were talking with them about, well, the president of the company we were talking with, and the president of our company said, well, that is a very operator dependent technology, dunking it underwater, very operator dependent. And the guy says, oh, our operators are totally conscientious. They are fantastic at what they do. Really, they care. And so later on, we went out, we were doing a tour, and we went to the area where the operator was putting the parts onto the fixture 2 at a time. And then the fixture would go underwater, and then the operator would turn around and dry off the parts that they just dunked, and then get them ready to set them in dunnage. By the time they turned around, the part was back up. It was coming back up. So really, they didn't look at the part at all, because it was a timed process, and it went down. They turned around, dried the part off, put it back. Well, our president goes over to this operator and says, "Hey, what are you doing here in this operation?" And she said, "Well, this is where I wash the parts." And of course, the president of the fuel rail company was, had one of those V8 moments there. So we operators don't always aren't always properly trained, and when we are dependent on them versus technology, there's some real consequences associated with that. Pressure decay testing. Here's a standard rudimentary fundamental pressure decay test, right? So we're going to pressurize the part. We are then going to isolate the part by shutting that valve off, and we're going to measure pressure change over time. So that is the fundamental aspect of pressure decay. Here is a pressure decay curve as an example. So the blue line there is pressurizing the part, and then we isolate the part. That's where that line comes in there, and then we measure the pressure change over a certain amount of time, and then that change in slope is what the instrumentation is going to do to determine, is this a good part or a bad part. So the no leak, as you can see, is the I'm colorblind. So is that a green line? Yeah, that's a green line, and then the red line is below it.
You got it.
What's that?
I said, yeah, you got it. It was green.
Okay, excellent. I couldn't. Yellow was it green? I wasn't sure. But green makes sense because it was a good part, right? So fill, stabilize, test, exhaust. These are the phases of a typical pressure decay application. So you're going to have a fill timer, you're going to have a stabilization timer. That's where you isolate, allow it to normalize, that pressure change in the part to normalize. And then the test is where you're actually going to measure pressure change. And then, of course, the exhaust is when you're releasing the air out of the part. So here are some of the influences. The volume variances are going to be a problem for pressure decay technology, because pressure decay technology is a volume dependent test. Anything that changes the volume of the part is going to be a problem, and anything that's going to change the pressure of the part during tests, like the adiabatic temperature effects, as we mentioned here, those are outside temperature influences on the part that can cause it to be a less than repeatable test and application. Again, we're just going through these quickly to kind of give you a warm up for the in-depth training that we're going to be conducting here in the next few weeks. Differential pressure decay leak testing. Again, this technology has really grown and improved over the last several years, and has proven to be a very, very good technology for testing those low leak rates. And it's also proven to be very good on large part applications as well. So, but differential pressure technology is we have a reference volume, we have a part, and we have a transducer essentially in between the two of them. And we are, instead of measuring pressure change out of the part, we're measuring a pressure loss out of the test part versus our reference volume. So we increase our sensitivity and reliability and repeatability with that application. Here is again just a gauge. We're going to keep rocking through this because we got to keep rolling. All right, mass flow leak testing. Again, this technology similar to pressure decay, only we are not going to isolate the pressurization of the part. We are going to measure flow into the part through a flow meter. So after the part gets up to pressure, so let's say it's 10 psi, so it pressurizes to 10 psi. we're going to measure the amount of flow that it takes to maintain 10 psi inside the part. So that's conceptually what mass flow leak testing is all about, is measuring the amount of flow that it takes to maintain a specific pressure inside the part. So here is a typical mass flow test curve. So we're going to, initial flow is very high because we're filling the part, and then that's going to, as the part gets up to pressure, it gets filled. Then we're going to measure that test over time. Of course, that variation narrows down as it becomes more and more stable. So here is a typical mass flow circuit where we've got, right now we fill the part through here because we don't want to fill the part through the flow meter. And then after the part gets to pressure, we isolate, and then we open up this valve here to allow the flow through the sensor into the part. So calibrating, again, I'm going to hop through some of this stuff. We need clean, dry air. We need consistent regulator pressure, or pressure regulation. Very, very important. If you have pressure that's going up and down coming into the mass flow instrument, then the results on the backside are going to be up and down as well. So ensuring that we've got excellent pressure coming into the part is critical. Sometimes if you have an upstream application, let's say you're torquing with a torque gun and it's using air, blah, 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 blah. Well, you're going to see that in your test technology if we're not properly isolating it and regulating the pressure into the part. In that case, we might want to put an accumulator in to minimize some of that pressure fluctuation. Differential mass flow technology, very similar to the pressure decay technology. Again, we've got a reference volume, we've got a test part, and we're measuring the leak out of the test part in reference to our reference volume. And so any leak out is going to cause pressure to go from our reference volume and into the test part. Then we got sniffer gas technology. This is something that Matt is extremely familiar with from his time with Infocon. But sniffer, we're going to pressurize the part with a tracer gas. In this case, we're saying helium. And then you're going to use a sniffer probe to identify, is there a leak and where is the leak? Rolling on here. So we've got, again, leak locations. We talk about sensitivity. Accumulation, I mentioned, we pressurize the part, and then we keep we have the part inside of a chamber, but we're not pulling hard vacuum on that chamber. We are just monitoring helium that accumulates. So that same sniffer probe that we're going to be using to do the sniffing is essentially inside the chamber, monitoring any helium level rise in that chamber. Hard vacuum, we're going to pressurize the part. We're going to pull a vacuum around that part, and that allows us to get significantly increased sensitivity because we are taking the background, what I call background levels, down very, very low. And so that increases the ability for us to detect small amounts of tracer gas leakage out of the part. So those are that is some of the technologies that we are going to be talking about and discussing in this leak test training. We'll also go into troubleshooting, how to troubleshoot pressure decay, mass flow equipment, and that is always a good reminder for our maintenance folks as well. So have a great rest of the day. We'll look forward to seeing you at our upcoming leak test training. Just go to capexsales.com to sign up for our regular email list, and then you'll get an invite to the training as well. Take care, everyone. Cheers.